All right. Welcome, everyone. Thank you for joining us for this seminar. It's my pleasure to introduce Professor Jeff Shamma. Of course, Jeff is not a stranger to this community. Jeff spent quite a bit of time at LIDS and got his PhD from LIDS and have collaborated with many of us, probably in this particular Zoom, on various problems in the past. His expertise is broadly in uncertain systems and robust control. He's done seminal contributions in slowly time varying systems in the past, and then later on transitioned to network and multi-agent systems. He's been looking at questions of learning and interacting with control and adaptation and what have you, both theoretical and in applications. And we're honored today to have him speak to us about his thoughts and how learning and feedback control interact. So Jeff, please.
Okay, thank you, Munzer, and thank you for the invitation. And yes, it's always great to get to come back to LIDS, and so thank you for this opportunity. Okay, so the title of the talk is Feedback Control Perspectives on Learning. And I'd like to start with a couple of acknowledgements. There are a couple of online videos that are really excellent if you can get a chance to see them. One is by Carl Aström. It's called Automatic Control of Perspective, and I'll be referencing that throughout today's talk. And then the other is called Respect the Unstable from 1989, and there'll be some references to that talk today as well. And I'd like to also acknowledge several people who kind of gave some nice comments in putting this talk together. Okay, so for a LIDS audience, this is not so necessary, but I'll just to normalize our starting point. The talk is feedback control, and okay, go. The talk is feedback control and perspectives on learning. So my definition of feedback control, if anyone asked, would be real-time decision-making in dynamic and uncertain environments. Certainly broader than the servo mechanism perspective. The usual kind of sequence is that a controller is interacting with an environment, and the environment senses the controller senses what's happening in the environment, makes a decision on what to do about it, and then takes action to try to influence that environment. And of course, it's been applied in a very large variety of different application domains. So I'll mention a couple of representative industries. In particular, the automotive industry is one where feedback control is prevalent. And really what the point I want to make here is that when we talk about a car, well, a car, of course, or an automobile is a system of systems. And there are actually many control systems built in to a single automobile. And here we have a listing of several of them. But there's feedback control is prevalent in any production vehicle in many ways. Another direction is the aerospace industry. And here we have a picture of the X-29 aircraft, which is an experimental aircraft from the 80s. And I'd like to quote here from the NASA website. It explored the use of a computerized fly-by-wire flight control system to maintain control of the otherwise unstable aircraft. And so fly-by-wire, it's a term that I guess we don't use anymore, but the point is that the pilot doesn't control the surfaces of the aircraft, but rather they speak to a computer, and the computer controls the aircraft, hence the fly-by-wire. Another point to make here is that traditional model-based feedback control has been performing at superhuman levels for decades. And there's been a lot of excitement about superhuman level performance recently with AI and machine learning, but at least in some domains and with feedback control in particular, the bar is much higher in that superhuman performance has been around. Okay, so as we mentioned, you can find feedback control everywhere, and it's generally an enabling technology. And here we're referring to Aström's talk. So you'll find a lot of synonyms for feedback control, even when control is not mentioned. So smart, active, autonomous, intelligent, self, this and that, guided. These are all indications that there's a feedback control in the box. And from Aström's talk, he says it's easier to talk about devices rather than concepts. And generally, people don't talk about the control until something goes wrong. And so here is a image from a dashboard, motor control system failure. This might be the first time that the driver sees the words control system. Okay, and the control researchers' lament is that when it's working, it's self-driving, and when it fails, it's a control system failure. And generally, you can just do a news search and find always a recent article where there was a crash and the words control system are appearing in the popular press. So this is a kind of a lighthearted example, but when it comes to safety critical systems, control system failures can be very costly or even tragic. So again, the title of the talk is Feedback, Control, Perspectives, and Learning. So what's the connection? And so in reinforcement learning, you have a learning agent, and the learning agent is interacting with an environment. So clearly you have this feedback structure. And also in multi-agent learning, let's set aside the environment. An agent is learning in the presence of other agents. And so the environment is the other agents who are also learning agents. But again, you have a feedback structure. And so feedback control is prevalent in whether it's single feedback structures are prevalent in either single agent learning or multi-agent learning. What I want to mention about the right-hand side picture in particular is that one has to be cautious in picking up learning approaches for single agents and dropping them into a multi-agent environment, because the environment is actually other learning agents. And being other learning agents, that means that it's a non-stationary environment. As I'm trying to learn about you, you're trying to learn about me. So your behavior today is different from what it was yesterday. So one has to be cautious in just applying learning methods to the multi-agent case. So what are our feedback control perspectives that we can bring to the table and the learning discussion? It can be analysis of feedback systems, design and synthesis of feedback systems. Here that tells us what feedback can do, but also I think it's good to mention what feedback can't do and to mention fundamental limitations as well of feedback systems. When I put the gallery, I should have figured this out. It's been a year into the pandemic, but does this block the view? Okay, or you see the full slide.
We see 3 lines. I see 3 lines.
3 lines. They're not cut off. All right. Okay.
Yeah.
All right. All right. So if we again refer to Aström's seminar, he mentions 3 benefits of feedback: stabilize and shape behavior, robustness to variations, and tracking command signals. And we're going to see how each of these translates to an issue in learning. So stabilize and shape behavior, we're going to introduce something we call higher order learning. Robustness to variations, we're going to introduce passive or monotone learning. And tracking command signals, we're going to talk about forecasting and its relationship to no regret. And we're going to use this example throughout the talk. It's a simplified example of flight control. We're only looking at longitudinal flight control. And the way this works is that the aircraft has a desired altitude. It measures the actual altitude, and then there's an error. And then the controller is going to act on that error by changing the angle of this one control surface, the elevator angle. And we can visualize that here by the aircraft just following the bouncing ball. Okay, so that's the desired altitude, and then it's going to use its control system to go up and down to follow the bouncing ball. All right, so let's start with the benefits of feedback. Stabilize and shape behavior, and that's going to lead to higher order learning. Okay, so the first illustration is without active feedback control, this aircraft will oscillate and eventually drift from a desired altitude. That's a behavior that we don't want, the oscillations and drifting. And so how can we use feedback control to let it follow the bouncing ball, and how does that translate into to an issue in learning? And as I mentioned, the main context that we're going to be considering is one of multi-agent learning in particular, where we have a learning agent learning in the presence of other agents. So let me give an example of such a feedback structure. So we have two players. It's going to be in the context of a game. The two players have their own utility functions. They have their own decisions. X1 and X2 are the respective decisions of player 1 and player 2. Each one is an optimizer. So we could have player 1 take a gradient step using its own utility function, and player 2 take a gradient step of its own utility function. And this happens over sequential stages. As we said, now they're in a non-stationary environment with respect to each other, but this is an example of interactive learning. And what happens when we apply this learning rule in different settings? And here's a simulation that illustrates oscillations. And so here we have a particular game. I believe this is just simple rock, paper, scissors. And this simplex reflects the probability of rock, paper, and scissors. And there are oscillations in this underlying learning rule. In the multi-agent case, we can have several players, all of them with their own actions, and each player has their own utility function. And the main thing that makes this a game is that the utility function of one player depends on its own action, but it also depends on the actions of other players. Special cases are when they're in the adversarial case, which is receiving a lot of attention recently, or zero-sum games. You have two players, and a benefit to one player is a detriment to the other. And there's something that we're going to call here allocation games. And the way allocation games work is that each player can allocate a fraction of its resources. The resources add to one amongst different channels. And there's different interpretations. We can think of this as allocation of resources. It also has other interpretations in terms of mixed strategies and subpopulations. I won't comment on those now. But the way allocation games work is that depending on the actions of others, we have different values of the channels, and then we assign a weight to our own to each channel. That's our allocation of resources, and add them all up, and that's our resulting utility. This is a special class of games that we'll be considering as well for this specific discussion. So now back to learning and feedback. A learning rule is just how do I update my own strategy as a function of the information that I have up to now. We already saw a learning rule. One was gradient play. I update my strategy using a gradient step using my own utility function, but my utility function depends on the strategies of others, which is also evolving. There's another learning rule, and the other learning rule works as follows. For allocation games, remember there's many channels, and I want to figure out how much resource to add to each channel. And so what we do is we compute the cumulative reward associated with each channel, take this integral. And so that's just how much reward has a particular channel offered since we started. And then my allocation of resources will be proportional to the exponential of that accumulation, or a Gibbs distribution. And so the more it has given over time cumulatively, then the more resources I'm going to give to that channel. And that's actually something called replicator dynamics. I have a handful of these tech fills, which I'm probably not going to cover, but for a controls audience, replicator dynamics can also be written in this more familiar way, where a channel gets more resources if its actual resource, if its value is higher than the average of all of the channels. But I'm going to skip these tech fills for this conversation. So now we're in the setting of multi-agent learning, and we like to know, how does a learning rule behave with different games? How do different families of games behave with different learning rules? And one question that's been asked for decades is, how can quote unquote natural learning rules lead to game theoretic solution concepts such as Nash equilibrium, where each player is optimal with respect to the actions of other players? As I said, it's been investigated for decades, and there are several monographs and overview articles on the topic. So I use this word natural, and what is the meaning of natural? Well, we're going to offer one characteristic of natural, and that is the learning rule of one player does not depend on the utility function of other players. So I might see what you do, but I don't know why you do it. And I'm going to update my learning rule maybe in reaction to what you've done, but again, not in reaction to why you've done what you've done. And gradient play is like that. I take an update that's a gradient step according to my own utility function, which depends on what you do, but I don't know why you do what you do. So it only uses my own utility function. Replicator dynamics is the same thing. I look at how much resource or how much utility that I have associated with different channels, which depends on what you do. It depends on your strategies. And then I allocate resources according to that cumulative effect on the different channels. It's a function of my own utility function. It's not a function of anyone else's utility function, although it does depend on other people's actions. So this is what's called uncoupled learning. And there was a very interesting paper from 2003 that introduced the following game. And the game works as follows. Each player has two actions, left and right, or probability of left and probability of right. Player one wants to be different from player two. Player two wants to be different from player three. Player three wants to be different from player one. And what they showed is that with this natural notion of uncoupledness, where I can react to what you do, but not why you do it, that all learning rules that are uncoupled do not converge to a Nash equilibrium of this specific game. And so it's a very sweeping statement that nothing can converge to the Nash equilibrium of this game just because it's uncoupled. Uncoupledness is very interesting here. Player one reacts to player two. Player one is not even aware of the existence of player three, which could say something about inverse reinforcement learning of if I'm watching player two, how am I going to invert their utility function, construct their utility function where I don't even know what they're looking at. The analysis is along these lines. If you looked at gradient play, and linearized gradient play, you'll find that it has zeros along the diagonal. And if it has zeros along the diagonal, then of course, nothing can converge to a Nash equilibrium. And the analysis for all learning rules, not just gradient play, is more sophisticated, but they showed anything that's uncoupled has this restriction. But it also has another restriction. All of the uncoupled learning rules look like this. The evolution of my strategy is a function of everyone's strategy and my utility function. And that holds with all of the different players. It's a function of my strategy and my own, and everyone's strategy and my own utility function. But and this is clearly uncoupled, but there's another aspect of this, is that the evolution of my strategy depends on people's current strategies, but not the history of their current strategies. And how can we exploit that history? So let's now make an analogy to feedback control. Remember we had a controller, and what I'm going to do here is I'm going to implement the controller where the aircraft reacts according to the current error, not to the history of the error, but what the current error. And in fact, what happens is it's unable to hold an altitude. It will start oscillating, and those oscillations will grow. And in fact, it's easy to show that for this setup, if you don't use history, then no controller can stabilize altitude. And that's a very analogous statement to what we saw with this previous result. Uncoupled learning cannot converge to a Nash equilibrium, but it's actually uncoupled learning that doesn't use history can converge to a Nash equilibrium. So we'll introduce something, we'll call it here higher order learning. And so here's our learning rule. Our learning rule is updated based on our own strategy and just some function of everything else. And we're going to introduce a proxy of that dependency on everything else that now also depends on history. How does it depend on history? Well, there's going to be some auxiliary states, and that's why we're calling it higher order learning. We introduce auxiliary states. So this something else, phi, is being processed by a dynamical system that we design to produce the proxy, and then we react to the proxy. Okay, and this is going to be a higher order learning rule. Something that we do in controls all the time is something like proportional derivative control, where instead of reacting to the error, we react to a myopic forecast of the error. And we can do the same thing with this proxy. We take history, and based on history, build this myopic forecast. And now let's react to that myopic forecast instead. And we can call this anticipatory learning. So it turns out that by introducing anticipatory learning, that one can overcome limitations that were thought to be due to uncoupled learning. It was uncoupled learning without memory, without history dependence. But rather, if you're going to do something like anticipatory learning, if the original learning rule was stable, then anticipatory learning will be stable. If the original learning rule is unstable, then anticipatory learning might be stable depending on the specifics. And so this is a illustrative simulation of back to that example of the anti-coordination game. Uncoupled learning without memory, they oscillates. Uncoupled learning with memory converges. So we see that it's not uncoupledness that is the issue here, but and for this particular game, it was the lack of memory. And I want to also highlight that we haven't introduced any new information to the players. If player one was watching player two, they just processed that information differently. One can do similar things for replicator dynamics and introduce something called anticipatory replicator dynamics. And one can change the behavior and say in zero-sum case of chaotic behavior to convergent behavior by having something called anticipatory replicator dynamics. And let's see, I'll skip this particular tech fill and also this one. I'll mention here with replicator dynamics, the growth of a particular strategy depends on the performance of that strategy, but in the anticipatory version, it depends on the predicted performance of that strategy versus the predicted performance average of all strategies. And so that's the anticipatory version of replicator dynamics, and it can turn chaos into convergence. And I'll skip this here. There are some interesting connections to optimization, and there's various notions of higher order optimization. And what we can do here is we can take what we called anticipatory gradient dynamics, where we don't take a gradient step, but rather we react to the anticipated gradient based on history. And this is what the differential equation looks like for anticipatory gradient dynamics. And if you do a step size and pick parameters in a certain way, I'll just jump to the end here. What you land on is what's known as optimistic gradient dynamics. And so in optimistic gradient dynamics, here it's very much written in a way that a controls person would appreciate. Of the new strategy is the old strategy plus a gradient step plus a finite difference of the gradient step. And we interpret that finite difference of the gradient step as a way of thinking about where the gradient is going. And so in that case, it looks a lot like anticipatory gradient dynamics discretized. And so that's an interesting connection. All right, so that was stabilize and shape behavior. And we saw that feedback control in talking about multi-agent learning can shape behavior from oscillations or chaos into convergence. And the connection was higher order controllers are like historical dependence on errors. I want to emphasize here that although we're controls people and we like to see things converge and stable and all that, that's not the main point. The point here is that there's a richness of behaviors and we'd like to understand exactly what can and can't happen under different constraints. And here we understand now that uncoupledness in itself might not be a constraint if we're willing to consider learning dynamics with memory. Okay, so now we'll move on to robustness to variations or passive and monotone learning. I can pause here for any questions before the second round.
So can I ask a question?
Yes, please.
So you're sort of alluding in some sense to having observers. I mean, it's not quite, right? Because it's unstructured, you have this cost utility function for the other people that you don't know, but somehow it's sort of, I sort of think that there must be some sort of observer version of this. You're trying to reconstruct something about them, some hidden states. And obviously the example you gave with the urban is like that, right?
Mm-hmm, mm-hmm. Yeah, you can think of, if you think of PID, do you think of PID as an observer? Or just using a recent history or using memory. So yes, there's something being reconstructed, but I think of observers more of there's a particular model and that I'm aware of, and I'm trying to reconstruct the state of that model. If we look at that 3-player case, player 1, as I said, was not even aware of the existence of player 3. Okay, so they're not trying to say estimates through an observer or an estimation algorithm, the utility function of others. They're not even aware of the existence of many of the other players. And so I think moving all the way to observers is a bit too much of a step, or rather is just admitting memory for now. Thank you.
Just a clarification, sir. Going back to the 18th slide.
Mm-hmm.
I remember you telling in this slide that you take a consideration of the current strategy and not the history. So that does that mean that you're implying Markovian strategy here for the scenario?
No, I want to emphasize memoryless. So here, this aircraft controls its position by changing this elevator angle. And what we're illustrating here is that if the angle is a function of the error, if the current angle is a function of the current error, then you're going to get oscillations no matter what. And what we'd say is that, can I make the angle a function of the history of the error? But if you only make it a function of the current error, then you'll never be able to hold altitude.
Something like a synchro system.
I'm sorry?
Something like a synchro.
Synchro, I don't know what that is.
Okay, I'll have it cleared.
Okay,
Thank you.
Thank you. Okay, so we'll talk about robustness to variations, and we'll introduce something called passive or monotone learning. So these are the typical equations for longitudinal flights, and there can be different variations when we're talking about robustness to variations. So variations might come in the way of external variations like wind disturbances, measurement noise, changes in the density of the atmosphere. But there might be internal variations. So you see here, there are certain parameters such as the mass of the aircraft or the different moments of inertia, the drag, thrust, lift. These are kind of coefficients within the state representation. So these kind of internal variations, we will call them parametric, mainly because we haven't introduced any new states. But there are also dynamic variations that would introduce new states. And so what could be sources of that? Say the airframe is non-rigid, say which is always the case. So you have non-rigidity, you have fluid structure interaction. I talked about a control surface moving up and down. Well, there's an actuator a motor that makes it move up and down, and those are not reflected in these flight equations as well. And so these are all kinds of variations, but the dynamic variations not only change the equations of motion, they introduce auxiliary states that we may or may not be aware of. In fact, it could be an infinite order system. And this is something that is very nostalgic to robust control types of how do we talk about robustness in the presence of variations where we don't even have a handle on how many states are associated. So a typical robust control question would be, does a controller, well, the nominal question, first of all, is does a controller have desired properties for a particular system that we're trying to control? The robust control question is, does a controller have desired properties for a whole family of systems? Okay, where we need not be specifying the order of those dynamics of in that family. And that's a robust control question. And now we're going to make a connection between having robustness to a whole family and learning rules. So let's recall what we called allocation games. The strategies of others get mapped into values for different channels, and we assign resources to each of these channels and add up those resources, and that's our utility. So a learning rule will take the different channels, process them, and then assign resources to each channel based on that processing. And then our strategies go through the game to produce the values of the different channels. So here we have a feedback loop of channels through learning rule to strategies, strategies through utility functions back to channels. And now that we've drawn it in this way, we're ready to start kind of having a home field advantage, at least because one picture looks like another picture. And then we'd like to ask a question: when does a learning rule work for an entire family of games? Okay, similarly to when does a controller work for an entire family of plants or systems being controlled? So the family that we're going to talk about here is something that was introduced about a decade ago called contractive games. And it's a lot to catch, but let's say we have strategies and we have channels, and a contractive game just has this inner product property. Okay, and it can be characterized by the utility function being negative definite over a certain subspace. And Hofbauer and Sandholm showed that contractive games are an interesting class of games because there are all these different types of dynamics: excess payoff dynamics, impartial pairwise comparison dynamics, and some others. They all are stable with respect to contractive games. But now what we're going to do is we're going to generalize the notion of contractive games and say that the strategies and the channels have this inner product condition over time. Contractive games, the original definition says that strategies and channels are negatively correlated pointwise in time, and we're going to ask that they're negatively correlated over time cumulatively. And we'll call that a generalized contractive game. And then we'll say the flip. The flip side is, this is what we'll call a passive learning rule. A passive learning rule is that the allocation, the flow of resources and the flow of payoffs are positively correlated over time. A generalized contractive game is the flow of resources and the flow of payoffs are negatively correlated over time. And you can see what's coming if you're in controls, and I use the keyword passive, is that these two are complementary classes. One is a learning rule where things are positively correlated. The other is a family of games where things are negatively correlated. And then one can state the following, that a learning rule stabilizes all games that are generalized contractive games if and only if it is a passive learning rule. If it's a passive learning rule, then it can stabilize all generalized contractive games. If it's not a passive learning rule, one can construct a generalized contractive game to destabilize it. And so I'm mentioning here that, yes, this is a connection to passivity, but instead of the input and output, it's a notion of passivity that uses the derivative of the input and the derivative of the output. And then I'll just skip that. So that's chapter 2, is robustness to variations. How can we talk about being robust to whole families of games? And this is a contribution in that way of saying that a learning rule has to be passive for it to be robust for all generalized contractive games. And so some discussion, you can think of these kinds of parasitic states or neglected states as the difference between, you think you're dealing with a Markov decision problem, but it's actually a partially observed Markov decision problem because they were states that were neglected. And there's always going to be neglected states. And then how can we talk about behaviors of games and characterize the neglected states in the presence of, or characterize the behaviors in the presence of neglected states that have some structure? Okay, so that was chapter 2, and I can take any questions here or move on to chapter 3, which will be tracking command signals. Okay. So we said the third benefit of feedback is tracking command signals. And again, I'll show a simulation here. And so the aircraft is charged with following the bouncing ball, and it can do a good job following the bouncing ball as long as the bouncing ball isn't moving too quickly. But if the bouncing ball moves too quickly, it does a poorer and poorer job of following the bouncing ball. So there's a presumption that there's a timescale separation. And we'd like to now kind of explore what timescale separation can mean for forecasting. So one type of learning in games in particular is I'm watching an opponent, and I try to make a forecast of what that opponent is going to do. And anticipatory learning was along those lines. Well, there's a very strong notion of forecasting called calibrated forecasts, and I'll try to convey the meaning here. So the usual story is with calibrated forecast is like forecasting rain. Yes, it's either going to rain or not, but the weather forecaster talks about the probabilities of rain rather than the actual outcome of rain or shine. So how would you know if a forecaster is doing a good job? That one test is just a simple consistency test, and that's called calibrated forecast. And the way it works is as follows. Let's take again with rain. This is a consistency test. Let's take all of the days that the forecaster said 40% chance of rain. What fraction of those days did it rain? And if over the long run, it's 40%, then they did well whenever they say 40%. Well, let's take all of the days where they say 50% chance of rain. What fraction of those days did it rain? If it's 50% in the long run, then they get a check mark on 50%. And if the weather forecaster gets a check mark on all of the forecasts that they're doing, let's say we have discretized forecasts, then that forecaster is calibrated. And what's very curious is that you don't need to know anything about the weather to be able to construct calibrated forecasts. And there are universal calibrated forecasting algorithms for which you give any sequence, even an adversarial sequence, and you can construct this kind of consistent forecast where whenever you say a particular probabilities over the long run, that will be the outcome. Now, generally, those algorithms require a discretization. So from 0 to 1, here we showed a discretization of 0.1, 0.2, 0.3, and so on. If it's an outcome that has 3 possibilities, then there's going to be a discretization of the simplex. But it turns out that there's a much simpler forecast that's not universal, but for special cases. And this is called the tracking forecast. So here's the function, here's what the tracking forecast, what it looks like. You see, it looks exactly like taking a recursive average. The new is the old plus the step size times the outcome minus the running average. But if gamma were equal to 1, that would be a running average, but gamma is a fraction here. This is what we're calling a tracking forecast. And then this step size is a large step size with respect to 1 over t plus 1. And so it turns out that if I'm watching a process that evolves relatively slowly to what? To the tracking forecast, then the tracking forecast can actually predict and produce a calibrated forecast of what that slow process is doing. So if you have a timescale separation between the thing that you're watching and your forecast algorithm, then your forecast algorithm will catch up to it and do accurate forecasting or calibrated forecasting, which is similar to the altitude tracking that we had mentioned previously. I'll skip this. And so here we're just showing an illustration of what happens when you use a tracking forecast and do a best response to a tracking forecast. I'm going to predict what my opponent is doing and then do a best response to what my opponent is doing with this tracking forecast prediction. And if my opponent is slow, then I should be able to predict exactly what they do. So these are 3 simulations that are no regret simulations. In the first, it's no regret versus no regret. And my cumulative utility is better than the cumulative utility I would have received using any one action. But if I switch to using a tracking forecast, my cumulative utility is actually strictly better than what I would have received using any one action, although it looks like it's converging in the long run and I don't have analytical results to show here. But if I use a tracking forecast against something that's called regret matching, where my opponent is using regret matching, it looks like it's strictly better over the long run. And so a main point here is, I'm not elaborating on what no regret means, but depending on the no regret algorithm that you use, all of them offer no regret, but they also offer different material performance in the presence of different types of environments. And it's known that if the environment is a reactive environment, probably the words no regret should better be phrased as no apparent regret, because it could be that I use even a different no regret algorithm and I could have done much better. So then I would have known otherwise. Okay, so that is the benefit number 3 of feedback, tracking command signals. And it relied on a timescale separation. And we saw that if I'm going to do something like calibrated forecasting for slow behaviors, then that's a timescale separation, and it makes a distinction with the type of no regret algorithm that I use, because you can use a tracking forecast or the other types of forecasts to do no regret. I'll skip this slide, which is kind of well known for controls types, and just state this recap. So we have higher order learning. It came out of stabilize and shape behavior. Passive and monotone learning came out of robustness to variations, and different types of forecasting algorithms and no regret came out of tracking command signals. The left-hand side is very kind of classical controls perspectives, and the right-hand side is how they can are related to learning. Now, these are all things that we've talked about on the positive side of what control can do, and I think it's worth pausing and thinking about what control can't do. And so there's something in control called the waterbed effect. And here again, I'll show a simulation. What the simulation is going to show is the aircraft trying to hold altitude when there's a disturbance. And there's going to be a low frequency disturbance and a high frequency disturbance. And the low frequency disturbance, it's doing a good job holding altitude. The high frequency disturbance is doing a bad job holding altitude. And the waterbed effect is, in fact, the better it does at one frequency range, the worse it will do at another frequency range. There's a trade-off, hence the terminology waterbed effect. What makes the waterbed effect worse? Well, if a system is unstable, then the waterbed effect is worse. Or if the system has non-minimum phase, and this is not the definition of non-minimum phase, but this is a characteristic. When the aircraft wants to go up, it raises its elevator, but that introduces a downward force. So to go up, it has to initially go down. Okay, and that's a non-minimum phase sort of behavior. And for non-minimum phase systems, the waterbed effect is even worse. And aircraft, this altitude holding example, it has that property. So how can you overcome this limitation? Well, there are actually impossibility results. So the impossibility results from the classical ones from the 50s and generalized in the 80s said that if I'm looking at a linear system with linear controllers, then nothing can overcome the waterbed effect. And what was interesting about the motivation behind these kinds of analyses is that it was because we don't have a lot of computational capability that we'd like to know what are limitations. But now when we do have lots of computational capability, I think that less attention is being made to these kinds of questions and say what can overcome these kinds of fundamental limitations. And in the 90s, there was a generalization that showed that the waterbed effect also holds for nonlinear controllers. So if there's a system that's non-minimum phase, like I just described, to go up it first go down, even using arbitrary nonlinear controllers cannot overcome the waterbed effect. The only restriction on these nonlinear controllers is that they can't tell the future. My control action today is a function of the past, not of the future. And there's a tech fill, which I'll skip. So here we'll make a final reference to Stein's lecture. And he introduced something, he didn't call it the waterbed effect, he called it the conservation of dirt. And that you can not really get rid of dirt, you can move dirt around. And so classical methods move dirt around in this kind of traditional way. Modern methods that have a lot of compute can move dirt around in this way. But there are certain fundamental limitations that cannot be overcome regardless. And I felt that it's important through feedback control perspectives to remember that we showed all of these things that feedback can do, to remember that feedback control, regardless of the type of controller that's being used, cannot overcome certain limitations. Okay, so the final slide. What we're seeing is a kind of an interesting interaction between a traditional controls community and traditional learning communities. There are new conferences, new seminar series. You're finding keyword commingling. You're seeing things like no regret for LQG, things that would not have been seen even a decade ago. So there's a lot of interesting mixing going on. there's an opportunity for mutual leveraging of successes or lessons learned, or rather, from both communities. And today, and instead of kind of showing a set of tools, rather, I wanted to show a set of perspectives, or inside reading the control researcher's mind as a control researcher might think about learning. And with that, that's all. Thank you very much.
Thank you, Jeff. This was a great presentation. We have time for some questions. Maybe you can unshare your slides so I can see people. You can either raise your hand or you just start talking. Well, I don't see any hands, so start talking. I have a question while people are thinking about this. So in the case of the multi-agent learning, as you made analogs to controls, maybe I missed something, but there are examples where the agent that is updating their learning strategy don't see the details of the agent, but rather the aggregate effect of the agent. So they have some, kind of network effect. So are these sort of general kind of analogs? Is there a way to think about this more as a distributed control problem? I mean, so what is the analogy there?
So some of the language that's used in the learning and games community. So we talked about uncoupled, where my learning rule is only a function of my utility function, but I have my utility function. I have the functional form, and I can do things like explicit gradients. And then there's a expression that was used called radically uncoupled. I don't know how the extent to which it took hold, but that's where I can only measure my utility as a measurement, but I don't have its functional form. And so, for example, in commuting, we can measure how much time it takes us to go from home to work, but I don't have a functional form as a function of the road that I take and the time of day and the cars that are on the road and what have you. And so there are analogs to everything that I've talked about, mostly everything that I've talked about. For example, in that 3-player game where there was an impossibility result, there is a utility version of anticipatory learning and anticipatory gradient dynamics, where I'm only measuring my utility, and that utility can be thought of as an aggregate effect, but I don't have access to the functional form. So there is a class of learning rules that are out there that only look at utility measurements. And controls community, sometimes that overlaps with the concepts like peak seeking, and those connections between peak seeking and finding equilibria of games have been made recently.
Questions?
Just to clarify, you had said that the strategy is actually dependent only on the information, and so let's say in a 3-player game that you had considered, are the strategies chosen by the 3 players independent of each other or dependent on each other?
So the strategy is a function of, let's say the strategy is my probability of going left or right, okay? And so I'm now how does that strategy evolve? That strategy evolves based on what I want to do by going left and right. So suppose I meet you in the hallway and say I'm trying to meet you, but you're trying to avoid me. So I might do left and right motions based on your motions, but not based on why you're moving the way you're moving. Okay, so I'm trying to meet you, you're trying to avoid me. If you were trying to do something else, anything else, my behavior would be the same because I'm not reacting to why you do what you do. I'm just reacting to what I observed you doing. And so that's the connection.
Jeff, how about stochastic gradients? I mean, in the case of RL, for example, I mean, people were able to show that doing stochastic gradients actually has nicer robustness properties in terms of generalization and so forth, in the sense that you don't really rely on the whole history, but you sample from the history. So is there now an analog to controls that we could think about that exploits these types of properties?
So some of these learning rules, not ones that I talked about today, have that stochastic sampling aspect of where I look at the finite window, pick certain events in the past randomly, and then do a gradient move with respect to those sampled events. And I'd have to think about how that's, that is a type of it's a type of memory dependence, but it doesn't have the kind of recency bias. Say, I wouldn't call it equivalent to anticipatory learning, because anticipatory learning has that recency bias of looking what's happened recently and using that to be a myopic forecast. But it is a type of memory for sure. And that could also be a way to kind of enable richer behaviors.
So in the you mentioned when you talk about passivity, in terms of arbitrary, adversary or whatever it was, you mentioned there that of course that's a special case of dissipativity. So just curiosity, have you looked at other dissipativity notions where there are similar theorems that you can do, small gain type theorems?
There has been a paper along those lines. So when in the connection to the game theory world, there's a there's a desire to connect it to decision making somehow. Okay, so if we look at the passivity condition that we had there's payoffs per channel and resource allocations per channel, and the passivity condition was that the flow is aligned, not that the two vectors are aligned, but that the flow is aligned. And so you can think of it like follow the money. Okay, as more payoff goes to one channel, then there's more resources allocated to that channel. Their velocities were aligned. Okay, now if you take something like small gain condition, one would have to, if you want to connect it to game theory, say, what does that learning rule mean? What does it mean for a learning rule to have small gain? What does it mean for a game to have small gain? Okay, or the complementary, whatever the complementary dissipativity condition is. So yes, mathematically, one can formulate this all as special cases of dissipativity, but it would be more valuable to make that connection of saying what does it mean for a learning rule to have a particular what's the word for that for sigma? What does it mean for a learning rule to have supply rate? What does it mean for a learning rule to have a particular supply rate? And when it's the inner product, it has a natural interpretation. Small gain, less so.
Got it. Thank you so much. It was a great talk, by the way.
All right, any questions? Comments? Okay, well, thank you so much, Jeff. This was a great talk and a nice nostalgia trip for some of us in the history of robust control, so we appreciate that. Anyway, Jeff is now the head of the Department of Industrial and Enterprise Engineering in Urbana-Champaign, so you can get his email from the website, and if you have any questions, please just fire an email to him directly. Thank you all for coming.
Thanks. Great being here. Thank you. Thank you. Bye.